This is Decision Maths 2 from 2021. The first question's a weird one. You're just being asked to put this into a linear programming problem. So, okay, firstly, you can't do this unless there's an n by n square. So introduce a dummy row or dummy column here. Put them all zeros because you're saying that essentially it's not going to take any work to do this job because there isn't a job to do. So just make them all zeros. And then what we're aiming to do, and you'd never actually write this down, but you're trying to make, you've got each worker and you want each worker to do one job. So if there's a 1 here, that signifies that A is doing job 1 and B is doing job 2, and so on. And if there's a 0, it means they're not doing that job. And it only takes one person to do a job, so there should just be a 1 in each row and a 1 in each column, and one of them only. And like you'd never actually write this down, but this is kind of what you're being asked to do. This might not be the optimal solution. In fact, it's very unlikely that it is. But what I'm just saying here is we're going to set up some variables that say xij equals 1 if the person is doing the job, and 0 if the person isn't, where I are the workers, so that can take the form A, B, C, or D, and J are the tasks, so that takes the form 1, 2, 3, or 4, even though 4 is actually just a dummy task. So okay, that's set up. And the objective, of course, is to minimize this times this number, plus this times this number, plus this times this number, and so on. So that essentially the ones will go in the smallest places that they can possibly go to minimize the whole thing. Of course, these two things don't have numbers in them right now. So what we're going to do is we're going to whack in some big numbers to make the minimizing problem essentially just never put anything here. So 1,000 would definitely do the job. And we'll minimize this function here. So minimize this times whatever number is here, plus this times whatever number here, which is going to be a 0 because this number is so big that it's going to want to put a 0 there, which is good because that he can't do this task, so having a 0 there is good. Plus this times this, plus and so on and so on and so on, all the way to the end. The zeros I've just skipped out because I couldn't be bothered to write plus 0a4 and so on. It just saved me a bit of work. So that's there. And of course, we're under the constraint that the sum of this row must be 1, the sum of this row must be 1, the sum of this column must be 1, and so on. So the sum of A with any j must be 1. Essentially, there can only be one 1 here, and there must be a 1. And the sum of B with any j is 1, and C, and so on. And also the rows. The rows must also do the same thing. So this sum of I1 and sum of I2 and so on must also be 1. And once you've done all that, that's the question done. Well worth learning that method. Usually it doesn't come on as its own question, but usually it seems like they do ask you to do this at some point. So well worth going through the book if you're a little unsure and doing that again. Decision tree then starts with a rectangle and then goes to a triangle if it's the end, a circle if there's some kind of probability aspect to it. So if you don't play, you just don't get anything. So that's fine. If you play, something can happen here. You can either get an 8 or more and you get £10, or you get less than an 8. This should be less than, not less than or equal to. Apologies. That should be a less than sign. In which case something else happens. Now, I've put a 5 here because it costs £5 to play the game. So if you spend £5 and then get 10, you're actually only £5 up, right? So again, this should be a less than 8, but what happens then? Well, you can choose. So again, there's another rectangle because it's a choosing thing. You can either not play again, or you can play. If you don't play, you won't get your £5 back, so you just lose that £5. If you play, another thing happens where if the same number appears on both the dice, you get £35, which isn't actually £35, is it? Because you paid £5 here and another £5 here, so you're actually only going to win £25. Or if you lose, you'll of course lose those £10. So okay, there's just some probabilities put in here. You can get out a very quick sample space. Actually, starting from this end, I guess. Same two numbers is of course 6 over 36. It's just a 1 in 6 chance. Not same, of course, is one take away that. There's of course 1, 2. The 6 cases here are 1, 1, 2, 2, 3, 3, and so on. So that's just 6 there and then that. This one is, I think, did I do this next? No, this one's slightly more complicated. A sample space would do it though. It's just looking for all the numbers bigger than or equal to 8. There are 15 of them, which means there are 21 that are less than 8. Again, that should just be a strictly less than sign. And then we work from this end backwards. So this times this plus this times this is going to equal that, which is actually better than this. So we'll choose that. If we get to this rectangle here, we will be choosing this option because it's better than -5. It's bigger. And then from here, I mean, not massively, but it is. And then from here, of course, it's this times this plus this times this. So apologies for this being a bit of a mess, which is this, which is worse than that. And so what we should do is we should not play the game and we'll have an expected monetary value of 0 if we do that. Good. Question number 3 then. So we've got, it's the transportation problem. So northwest corner, so we'll put we'll put this station P needs 25. station A can give 28. So we'll give all 25 to it, and that leaves station A with 3 left over. So we'll go across and put a 3 here. Station Q needs 41, so it needs 38 more, which you can get entirely from B. So that's good, that's done. And we're good. B has 5 units left over, so we'll move those over to R, which needs another 35. So we'll shove all 29 of C in there, and it still needs another 6 or so, doesn't it? So we'll put 6 of D in there, and then D has 30 left over, which is great because S needs 30, and we'll end up with our northwest corner set up. Next then, so it says taking AS as the entering cell, so put a theta in AS. Let's make this better. If a theta is here, for this row to still add up to 28, we're going to need to take away a theta, but we don't know which to take it away from. So actually we start with this column. So 30, for the same reason this column always needs to add up to 30, we've randomly introduced a theta, so this needs to be 30 minus theta to make this still add up to 30. And then here, this needs to be a 6 plus theta to make that still add up to 36, which it should do. And then here, we don't know which of these to reduce, maybe, because we've got 2 numbers here. So what do we do next? Well, we just say that's 29, and I'm trying desperately to remember why we just call that 29. Why do I not move that? Well, of course, if you make that 29 minus theta, there's nothing else in this row, so there's no way to add a theta back into this row without adding another entering cell, which you're not allowed to do. So we must reduce this one by theta to balance this column here, and then add a theta into this one to balance this row, and then take a theta from this one to balance this column, and then this column is balanced, so this just becomes the same 25. So that's how we set that up, and we're trying to make every cell positive, obviously. So the biggest we can make theta is 3 to make this one 0 here, and if we put in theta as 3, we get this magically. You can check my maths if you want to, and this will be our improved version. So I'll stick that here, so that's the improved version here. I've now lost the initial one because I don't care about it. And we're being asked to, from scratch, improve this one as well. So let's get out this cost table here. So this is the costs of the cells or the routes that I'm actually using. I'll put them in red. Usually you X them out, but I prefer just writing them in red so that I can just do everything looking here and I don't have to look up here too much. So start with a 0 here for the shadows. This makes an 18. 0 plus 18 is 18. This makes a 13. 0 plus 13 is 13. Of course, that makes this one down here an 8, I think. 8 plus 13 is 21, which makes this an 11. Keep going. So this one's next. Make that an 11. Then this one make a 3. Then this one make a 12. And now that you've got all your shadows, now you can do your improvement indices by doing this number here, whatever's there, 19. Take 12, take 0 is 7. And then likewise, 17, take 11, take 0 is 6. And then 16 here, take 18, take 3 is minus 5. And so on. Do that for all of the remaining ones, and you get all these numbers. You can check my maths again. If you see any negatives, then that means the solution isn't optimal. There are quite a lot of negatives here. We're going to choose the biggest negative, so minus 10. So go back to your table over here and put a theta in minus 10. And now we're essentially starting from this point where we now know our entering cell. Our entering cell is DP. And we'll do the same thing again. So we need to take away 20 theta from this 25 to balance this column. We need to add it into this 3 to balance that row. We need to take it away from this 27 to balance that column, which also fantastically balances that row. So all the other numbers can just remain the same. And we're good to go. The biggest we can make theta here is 25 this time. That makes this a 0. 25 here, 2 there, and 28 there. So that's going to be our new improved matrix. And the entering cell was DP and the exiting cell was AP, which they always just want you to write down, so don't forget. And the state the cost, well, it's going to be 25 times 16 plus 41 times 15 plus 2 times 14 plus 29 times 22, and so on. And you get that cost there. Determine whether this is optimal. So once again, this is the improved table. We'll do some shadow costs. So I've written in the cost of each route that I'm actually using. Start with a 0 here, even though there's not one here. Start always here. That makes this a 13. That makes this an 8. This is very similar to what we did before. That makes this an 8. That makes, what else can I do? That makes this one an 11, which makes that an 11, which makes that a 3 as well. And that one there is a 12. And then do the same thing. So 18 take 8 take 0 is 10. 19 take 12 take 0 is 7, and so on. Do that for all of them. If they're all positive, then it's a optimal solution. Now in this case, they're not. This one is negative, so this is not optimal. And we just have to state that we've got a negative improvement in Z, so it's not optimal. We could improve this. Good. Now it's the recurrence relation question. So this is a very easy start here. We're just going to say from here, we could kind of convert, well, okay, I started here. I guess you could do either. we started here, I converted this to n plus 2 and this n plus 1, so I'm just setting n to be n plus 1, I guess, to increase those. And then, of course, I can substitute this result here for y n plus 1 into this result here, expand out and collect, and you'll end up with what they wanted you to get. So that's that done. Solve this now. So we're going to deal with this bit first and set up the auxiliary equation, which is m squared minus 6m plus 8. That has two solutions. This is one of the first projects you ever learned to factorize, so maybe just do that. M is 4, m is 2, means your complementary function or solution is un equals big A, don't know what A is, times 4 to the n, plus big B times 2 to the n. We'll solve for A and B later. For this bit here, you just set un equal to lambda, because it's just a constant and neither of these are 1. So you can just use lambda. If these were 1, you could use lambda n. They have tested that before, but sure, we just use lambda here. And of course, we're going to shove this into here. Now, un plus 2, I should have called this xn, sorry. I think I've made that mistake throughout, sorry. I've called this un just because I'm so used to using them, but it should be xn, so apologies for that. But yeah, this should be an xn, this should be an xn. You put this result into here. Now, xn plus 2, or un plus 2, is still just lambda, because lambda doesn't depend on u, or n, sorry. And so this is still just lambda, and this is just lambda, so we end up with this, which very quickly gets you to that. And so this is the answer here, where lambda is just 1. So you've got the complementary function there, and the particular solution there. Again, this should be an xn, but it's not really going to matter too much. I just missed that. Anyway, from here, we can use the initial conditions. X1 equals 1. So we're going to put 1 in here and replace this with a 1. Again, just pretending xn equals un, I guess, for purposes of this. That makes 4a plus 2b plus 1, but the 1's cancel and you can divide by 2, you get this. Now, this one's slightly hard to deal with. y1 equals a means if I put n is 0 in here, I'll get y1 equals 3x1 minus 4x0, but y1 is a, so I can replace that with an a. But I also know x1 is 1, so I'll replace that with a 1. And x0 is what happens when you put 0 into here. Into here, of course. Put 0 into here, and you just get, well, that's 0. Sorry, that's 1. That's 1. So you just get a plus b plus 1. And you can rearrange that to be this. And now we can use these two results, right? So I think I rearranged this one to be that. And then I replaced this b with minus 2a, which makes that plus 8a. So I got this, and that led to that. And then, of course, you can just times that result by minus 2 to get that. And then this solution here, you can write with this a and this b, and you'll get this. Again, this should be an xn, but I've said that enough times to just move on, I think, now. So that's that done. X7 or U7 is this. So just put 7s into here. You've got a calculator, so there's no reason to be particularly intelligent about this. 4 to the 7 divided by 4 is 4 to the 6, which is that. 2 to the 7 divided by 2 is 2 to the 6, which is that. Expand out, or just, you don't actually expand out, just do this, take away this, right? Because this is the same thing. And you get this, then divide by that, then take 1, you get a is 6. Good. Question number 5 then. Now, I've withheld giving you this information for a while, but this paper was the worst exam that I've ever had to do on YouTube, because Edexcel, Pearson Edexcel, forgot to attach the answer booklet to this paper. So, it was kind of okay until this question, but this question, having no answer booklet for this, having no pictures to use, you know, if I ever become a really big YouTuber and, you know, get really popular and famous, and then it goes to my head and I become like this massive jerk, and then future YouTubers are making videos about the downfall of R2D2, they don't have to do any research. I'm telling them right now, those people who are going to make that video, I'm telling them, this is where it started. This is where the downfall started. This is where I became an absolute jerk to everyone. Because this question took me so long to do, to try and fix their mistake of not including the answer book to one of their exam papers. Dear God, this took a while. So it started off okay, C1, right? You just add together the maximums if it's going left to right, which in this case it always is. So 8 plus 11 plus 8 plus 10 plus 6 plus 2, which is nice and easy. Or you take the minimums if it's going the wrong way, like this one is. So this is going to be 8 plus 17. Take away this 4, because that's going the wrong way. Also take away this 0, which obviously isn't doing, because that's also going the way. Take away this 1, and then add this 30, add this 2. So that makes 52, and that'll be there. Using the capacities, what can be deduced about the maximum flow? Maximum flow minimum cut theorem. This cut is 45, so the maximum flow cannot be bigger than 45. It must be 45 or less. So that's good too. Next, it sets up this network for you. And it says state the value of initial flow. That's just 5 plus 11 plus 6 plus 14, which I believe is 36. I hope it is. It looks like it. Good. And then by entering values along this, complete the labeling procedure on diagram 1 of the answer book. So there is no answer book. So I had to draw this whole thing using arrows in PowerPoint. And then I labeled every single thing except for the 3 that I'm going to get 2 marks for actually labeling. Let me just talk you through maybe how I label these and how this works. If you've got a current flow of 5 through S to A, and this is the capacity for S to A, that means you could increase the capacity by 5, that's where that 5 comes from, or you could decrease it by 1, and that's what the backwards arrow 1 means. So another example is up here. This is currently 5, and it's a 5/8, so you could increase it by 3, or you could decrease it by nothing, and that's where the 3 and the 0 come from. So that's what we're doing to set up this whole thing. And then BC, so a couple more examples then, B to C. So BC is 2,5, it's currently got 2, so it can be increased by 3 going to C, so that's going to be a 3 here, and it cannot be decreased because it's currently already at the minimum, so 0 going backwards. And then this way, it's currently 20, so it could be increased by 2 and decreased by 2. And then this last one was down here. This one here cannot be increased, so that'll be a 0 going forwards, and it can be decreased by 2, so the 2 going backwards. So that was, I crossed this out and gave myself 8 marks for doing that. So this paper was out of what, 81 for me? So 81 out of 81 is going to be good. I doubt I've even got 4 marks though, because I never do really, do I? Use the labeling procedure to find the maximum flow through the network. So what we need to do is we need to study this thing quite carefully and just find some optimizations. So for example, I mean, it starts at S, finishes at T. Can we find a route that gets from S to T where we've just got lots of 4-add arrows with lots of numbers in them that we can just use? So for example, this to this to this to this, that's 5, 3, 6, 3. So that's saying this could be increased by 5, this could be increased by 3, this could be increased by 6, and this could be increased by 3. Now we need to use the minimum of those, obviously, because just because you can increase this one by 6 doesn't mean you can increase this one by that. So let's increase all of that path there by 3. And that lowers that by 3. Now, the reason that lowers that is because imagine we've changed that to an 8 now. Now, there's only 2 more that could go through it, and you could go backwards 4. So essentially, I just increased that by 3, decrease that by 3, and increase that by 3. Right? And same here, increase that, decrease that by 3, increase that by 3, and so on, all the way around. And that means this route increases it by 3 for me. So that's good. Can I find another route? Well, I can't go to B. I've got zeros now. So let's go, I think I chose to go across now. So across here, across here, across here. Looks very simple. I think I can just increase all that by 2. Is that what I did? Good, that's what I did. Yeah, just increase that by 2. So increase by 2, increase by 2, increase by 2, which actually means decreasing this by 2 and increasing that by 2, increasing that by 2, increasing that. Because of course that's saying there's no more now that can go through that. I've changed that to an 8 essentially. So there's no more extra I can put through that. And now can we find any other route? Well, it's got to go down here, right? It's got to go down here. It can't go through here or here, so it's got to go up here. Now this looks a bit weird because it can't go down this way. It's tempting to think it go this way, but actually that's a backwards arrow. So can we go through this way when it's a backwards arrow? And the answer is, actually, yes, we can. Just like Barak said, yes, we can. We can go through this even if it's backwards. Because what we can do is we can say, okay, let's increase this by 2, increase this by 2. That means there's 2 extra flow going to C. If we turn this one down by 2, that means there will be 2 less going into C, and that will balance out C. Now that means E is unbalanced. It's got too few going out. So let's increase then this one by 2, and that'll balance E as well. So we can increase, decrease this one in this direction, and then increase that one. They can all go up by 2 because that's the most you can change that one by. And we'll get another route, and we can change all those arrows in the way that we usually do. And we'll get another route, and that will increase it by 1, 2, 3, 4, 5, 6, 7. From the 36 we had, gets us to 46, and 43. And this is this is just the answer to the thing. So we increased this path by 3, didn't we? That was the first thing we did. So that all increased by 3. That's only gone up by 2. Why is that only gone up by 2? That's confusing. I thought I increased that one by 3, didn't I? I thought I increased that one by 3. So why is that one only gone up by 2? It's just the answer from the booklet. So maybe they did a slightly different. I think what they will have done is they did a slightly different set of 3 improvements that got them the same result, and that's why they've got a slightly different labeling procedure here. So let's ignore this. This is just from the answer book because again, there wasn't an answer booklet. This is just from the mark scheme because there wasn't an answer booklet. So I just copied it, but it's actually not correct, is it? So what we'll say is what we did was we increased this root by 3, so add 3 to all of those numbers. We then increased this root by 2, so add 2 to all of those numbers. And then this root, this was the complicated one, we add 2 to those numbers, take 2 from that number, and add 2 to that number. And then I think we should end up with our answer, whatever that looks like. But that would be our answer. And it's slightly different to this because we used a different algorithm, or the mark scheme used a slightly different approach for that answer there. Anyway, continuing, prove that answer F is optimal. When you're doing a proof question in flow things, it's always about finding a cut. Find a cut that's 43. Eventually, if you search hard enough, you'll find this because this is 8 plus 11. This is going backwards, so minus 2, minus 4, plus 22, plus 6, plus 2, and you'll find 43. So therefore, by the maximum flow minimum cut theorem, 43 will be the maximum. A vertex restriction is now applied to B, so no more than 16 can flow through it. Complete diagram 3. So I had to draw this. So this is roughly what I assume diagram 3 probably looked like. But what we do essentially is if you've got some kind of restriction on a vertex, you just extend that vertex out into an in and an out section, and you say it's basically its own arc that can have a minimum of 0 and a maximum of this 16 here, and that's basically all you have to do. State the value of the maximum flow within this restriction. Well, there's only 1 mark for this. I'm assuming this was 2 marks, and this is probably 1 mark. So I think we can get away with being as lazy as just to say, well, in our optimized solution, we needed 19 to flow through B, I think. That's 19 in total. So if we decrease that to 16, that just decreases this down to 60 to 40 as well. We just decrease it by 3, and I think it's possible that there's a way to augment it so that it doesn't actually decrease by 3. But if it's only 1 mark, I think you can probably just play it safe and just say they're not asking me to do that much work. They're just asking me to do that. Okay, excellent. Question number 6 then is the dynamic thing question. This is a problem about minimax. So he's trying to minimize the maximum he'll ever have to travel. So he's starting here, he's finishing here. And basically what he wants to do, what this says here, is he wants to find a route such that he never has to do any massively long journey in one day. So basically he wants to avoid these 53s and 52s, right? He doesn't necessarily want to do the shortest journey across the entire thing. Like maybe there would be a journey that was like 1, 1,000, 1, 1, and that might be, well, that wouldn't because 1,000 is too big, but like 180, 1, 1, and that might be the shortest route across the entire thing. But it involves an 80. That involves a lot of cycling in one day. He wants to find a route that would avoid any big numbers at all, even if the average is bumped up slightly because you're doing quite a few fairly long routes rather than just one really big one. Anyway, that's what minimaxing is about. So now use dynamic programming. So we'll start, obviously, we'll call this stage 1 here, this kind of row, Hij. We don't need to start here because it's the end. So we'll start here. And we'll say from H, you can just do H to T, or from I, you can do I to T, and from J, you can do J to T. That, of course, finishes all at T. And those distances are 47, 48, 49. So nothing interesting to start with. Dynamic programming always starts off very boring. I mean, as if it ever gets interesting, but it always starts off at least very boring. Stage 2, you can start at D. Stage 2 is this column here. So from D, you can do 2 things. You can either go H or you can go I. So we'll just label those. And H is 49. And if you go to H, your next route from H is 47. And the maximum of those 2 things is 49. And then if you go to I, it's 50. And then from I, it's 48. And the maximum of those is 50. So what we're saying here is if you're at D, the maximum is if you go this route, is the longest day's journey will be 50. And this route, the longest day's journey will be 49. Now, 49 is the better of those because, again, we're trying to minimize any really long days of cycling. So if he goes for this route, sure, I mean, it's actually shorter in total as well, isn't it? But even if it was longer in total, because he avoids this biggest single day cycling here, that's his preferred one. So we're minimizing the maximum route, minimax problem. Anyway, for E then, we're going to H, I, or J. So there's sorry, no, it's not. It's just, we can't go to I. It's just H and J. And that's 51 and 46. And then of course, from H, it's 47. And then from J, it's 49. And then the maximum of those 2 things is 51 there and 49 there. And the minimum of these is 49. So if he's ever at G, he's going to want to go down here to avoid essentially to avoid this 51 here. From F, that looks like, do the same thing. So we can go to H, I, or J this time. And that will take 51, 52, or 50. And then, of course, after you get to H, that's a 47. After I, that's a 52, and then a 48. So you can actually just read the diagram, or from here, it doesn't really matter. And then 50 to 49. And the smallest size is 50. So if you're at F, you would choose to do the J route, because that has that avoids the 52 and it avoids the 51. And so you have the shorter days in general. From G then, we've got these two options. The same thing happens. It's the same idea. You choose the smallest. And then it gets slightly more interesting when you get to stage 3. Now, thinking about A, you can either go to D, E, or F from here. Now, to D, you're looking for the maximum of 53, and whatever route you've chosen from D. So from D, we know there's a route where the maximum day is 49, so we'll go with that one. And from E, so A to E is 52. From E, we know there's a route where the maximum is only 49. And again, we'll go for the maximum, which is 52. It's just the A to E bit. And to F is 53. And from F, we know there's a route that says 50. But again, we need to choose the maximum of these. And the maximum of those is 52. So actually, because it's quite a long way from A to anywhere, you probably just want to avoid A in general, because it kind of makes useless all of this good work of finding some good ones up here. But anyway, from B, same idea. We've got an E, F, and G. We get these results, and the smallest is that one. So from B, there is a route that avoids anything bigger than 50, which is good. So it looks that's pretty good. That's better than going through A for sure. And then from from C is the last one in this stage. We've got two routes. It's going to be this and this. Smallest is 50 as well. And then finally from S, you have no idea how annoyed I was that there are 3 rows that I'm going to have to enter for S, and I only had 2 columns left. But in any case, it's going to be 52, and then the minimum, the minimum from A is 52 as well. So, and of course, the maximum of those two is 52. To B, it's 48, and then the minimum from B, the best case was 50. So that's value 50, and then C is 50. And then we can also do from C, we know there's a route where the biggest is 50. So these two are the optimal ones. We can go from here to here, only going on a maximum journey in one day of 50. And we can avoid all the 51s, 52s, and 53s. We can actually do it in 2 different ways. We can either start at S and go to C, and then from C we go to E, and then from E we go to J, and then from J, of course, we go to T. So that's that route. Or this one here, this one here, we go to B first, of course, S to B, and then from B we go to F, because that's got the star. From F we go to J, and from J, of course, we go to T, and we'll have that route as well. Thank you so much for watching. No, wait, oh my gosh, question number 7. It feels like I was done, but now there's a game theory question. And guess what? The answer book would have come in handy for this as well. So great. Alexis and Becky are doing a thing. So this is a table that I managed to copy and edit from the mark scheme. So we're going to enter into this table. This is, I assume, what the answer booklet would have looked a bit like. Now we've got something interesting going on here. So this here is created by the idea that Becky plays X, right? Alexis's winnings are 6 times the chance of her playing Q, and then 1 times the chance of her playing R, P1 and P2 respectively. However, you don't just put in 6 and 1 here. I mean, these next ones are the same, right? So it's tempting to put 6 and 1, 8, 0, because of course there's no P1s, and 8, and then 4 and 2. But look up here, V is the value of 3 plus the value of game of Alexis. So actually what we need to do is we need to take away 3 from all of these things, because what they've done, so I've just taken away 3 from everything there. What they've done is they've taken this table here, and to turn it into a programming algorithm, they've added 3 to everything to make it positive, and then they could apply some X. So we're just undoing that. We're going to take away 3 to get to here as well. So that's that completed. Use a graphical method to find the best strategy for Alexis. So, okay, what we need to do is we need to say this one is 6 P1 plus P2, but we know P1 plus P2 basically equals 0, which means P2 is 1 minus P1, which means we can sub that in there, and we'll get this, which equals that. And we just need to draw this as a line. And we'll do the same thing for this one. 8P2 is just 8 lots of 1 minus P1. You could, of course, rearrange for P2 instead and draw that, but we get this, and then this one here. Again, one last rearrange to do, and we'll get this. And these are the 3 lines we need to draw. I assume what was in the answer booklet looked a bit like this, I guess. This is the best I could do. This is P equals 0, this is P equals 1. And so we can draw these fairly easily. If we start here, for example, when P1 is 0, we just get 8. And when P1 is 1, we just get 0. So that's a very nice, easy line to draw. This one, when P1 is 0, you get 1, and then you get 6 when it's 1, so you just go from 1 to 6. They've given us these helpful dashes. Again, this was just from the mark scheme, and I just edited out the answer. And then lastly, we just put P1 is, when P1 is 0, we get 2, and then we get 4, so it just goes from 2 to 4. Now, we're looking for one of these intersections, obviously. How do you know which one it is? What you do is you start on this corner here, and you just highlight the lines going along the base of the picture. So this to this to this. And you're looking for the highest intersection in this kind of picture here, which is this one here, which is the intersection between this line and this one here. So we set those equal, and we'll find P very quickly, P1, I should say, which of course means P2 is 1 minus that. And we'll have our two probabilities, which is great. Calculate the value of the game. There's a couple of ways of doing this. You could just shove this into there, because of course the value is essentially this bit here. So just shove this P1 into there. 2 times 3/5 is 6/5 plus 2 is whatever that is. Or alternatively, you could put both of those and you could put them into here and choose, importantly, choose the least. Of course, these two end up being that 3.2 value, because those two are the ones that actually collide to make that 3.2. This value 4 is talking about this line, which is irrelevant to us. So that's why that's there. And that's also why these V's are less than or equal to, because this 4 is essentially irrelevant. We want to be the lowest we can get here, which is 3.2. Anyway, that's the value of the game to Alexis. Becky intends to make a random choice, probabilities Q1, Q2, and Q3. Determine the best strategy for Becky. Now, there's a couple of ways you could do this. The first thing you could do is you could just do the opposite to this, right? So this was reading down the columns to make some stuff for Alexis's payoff. We could read across the columns to do the same for Becky. So Becky's winnings, we can say here, are 3Q1 minus 3Q2 plus Q3 equals 0.2. Now, there's a couple of things I've done here. Firstly, in game 3, you read Becky's point of view in the opposite to Alexis's. So this actually represents Becky losing money, and this represents Becky winning. And of course, in a zero-sum game, which is what this is, Becky's payout is actually minus 3.2 if Alexis is positive 3.2. Should I have taken away 3 from this? Yeah, I should have, right? Have I already taken away 3 from this? Yeah, I should have taken away 3 from this and said this is 0.2, because I never actually did that. I've taken away here because I'm working with this table, so I knew I was going to. But this is 0.2, not 3.2. Apologies for that. That's definitely a 0.2. That's annoying. Anyway, so this makes 0.2. Of course, if Alexis's winnings is 0.2, that means Becky's a minus 0.2 because it's a zero-sum game. But of course, if I just pretend those aren't negatives, I can pretend this isn't either. So I could have written this as minus 3(1)Q2 plus 3Q2 minus Q3 equals minus 0.2. But of course, the negatives will cancel and I get this. And of course, you can do the same for this row, and that also equals the same number. And then, of course, you can say the Q's must add up to 1, and you can put that in a calculator, and you can just sort out that the answer is this. The other way to do it is perhaps slightly more intelligent, is you can say, well, okay, looking at these 3 answers here, this is the payout for Alexis if Becky plays option X, which is bigger. So basically, from Becky's point of view, that means Becky should never play option X, right? She loses more money. So we can just look at this and say Becky shouldn't play option X. We can just say Q1 is 0, and we can just say that. Which means, of course, then we can read across and just make a nice, easy 2-dimensional simultaneous equation, which we can easally solve by adding these together and finding Q2, and then finding Q3 from there. And then we just maybe write at the bottom here a little sentence about to actually answer the question, and we will actually be done with that paper once we've done that. Thanks for watching.